All right, good morning, 8th grade science class, both in person and online. Today we're going to be going over our day 3 of the 8th grade science star review. As always, remember to put your name up at the top and put the date. That way when we go back through and check, I can see the days that you completed it on. And if you didn't complete it in class, I'll understand why you made more mistakes and I can get to you and help you out, okay? But make sure you're always putting the date up there. All right, so we're going to start off with number 1. Now, all of these questions are going to be about chemical reactions and chemical changes, but it's going to be about observing those chemical reactions and seeing signs of a chemical change. Now, remember, a chemical reaction is when a chemical change occurs, and a chemical change is when you have a brand new substance. You no longer have the original substance, you have something completely new. And you can't get that original substance back, all right? Now, maybe in a laboratory setting, really carefully you could try, but it's going to be very difficult to get back your original substance, and in most situations you cannot. So number 1, Felipe observing how acetic acid or vinegar and sodium bicarbonate or baking soda react with one another in a volcano model. If you ever created a volcano as a science project, this is just what we're talking about here. So what evidence can Felipe look for when indicating a chemical reaction to indicate a chemical reaction has taken place? So the key word there, guys, is chemical reaction. So A, B, C, or D, one of these is going to be a sign of a chemical reaction taking place. And remember our signs of a chemical reaction, things like color change, unexpected color change, unexpected temperature change. Things like bubbling or fizzing means that a pressure change occurs and it's creating those bubbles. Production of a precipitate, when two liquids come together and form a solid, that's called a precipitate. That's a sign of a chemical change. All these are different signs of a chemical change. So let's kind of use our process of elimination and go through them here, all right? So the volume of the acetic acid increased. Now, volume is how much space you take up. A change in volume could be a sign of a chemical change, right? Because it's increasing. It could be if two liquids went together, right? And they mixed up and they formed into maybe a larger solid. That could be something, but volume change could be a sign of a chemical change. So we're going to keep that in the maybe pile, okay? Now, the density of the baking soda increased. Now, as the baking soda starts to soak up vinegar, that density will be increasing. So we're going to move past that one as well, all right? Gas bubbles are produced. Remember, production of gas means that a pressure change is occurring, and that's a clear sign of a chemical change. And then the baking soda is dissolved. So dissolving, evaporation, freezing, those are all signs of a physical change, because if you really think about it, you still have the original product. That baking soda dissolved is still just baking soda in whatever substance it's dissolved in. And if you take that other substance out, you'll still have baking soda, okay? But the only real sign of a chemical change here is C, gas bubbles are produced. All right, and that's because dissolved is not, okay? Then it's because density of the baking soda, all right, density doesn't have to do anything with chemical. And our volume, all right, not gonna have anything to do with our chemical reaction. But those bubbles being produced, clear sign of a chemical change, right? Number 2, during a science lab, Jessica records the following data. When a clear liquid A is combined with clear liquid B, here are the things that happen. Temperature didn't change for over 5 minutes, all right? So for over 5 minutes, nothing happened, but temperature did eventually change. But that could just be due to the room temperature in, the environment that you're in. Could be getting a room temperature, okay? Color change. A yellow liquid is formed immediately. Remember, an unexpected color change is a sign of a chemical change. State of matter, no change in the state of matter. No liquid to solid, no solid to liquid, okay? So no change in the state of the matter. Why did a chemical change occur, guys? We know that one of these is going to be a chemical change, this one right here, color. But why did it occur? So we can automatically take off the no, because yes, a chemical change did occur. But why did it occur? Okay, so yes, a new yellow liquid is formed, or B, yes, mixing any two known liquids will cause a chemical change. Guys, any two unknown liquids? No. If you took Sprite and water and mixed together, what'd you get? Watered down Sprite. No chemical change taking place. The bubbles that you would see in the Sprite is just a pressure change from the actual carbonated water. That's not a chemical change. And a good example is that when you open a can of soda, you hear the psst, and if you listen real closely, you can hear bubbles. But it's still just soda, right? When you taste it an hour later and it's flat, it still tastes like that soda, then no chemical change occurred. You just lost the carbonation, you lost the pressure, okay? Always remember, guys, look for multiple signs of a chemical change. If you only see one sign of a chemical change, you can't really be sure that a chemical change is taking place. But if you see multiple signs of a chemical change, you can guarantee it. All right, so our answer choice is A. Because of an unexpected color change. It turned yellow. Two clear liquids turning yellow. You wouldn't expect that. Okay. All right, number 3. A science class places a rod outside, all right, and they place the rod inside in a sealed container. Then several weeks later, they go outside and they see that the rod has rusted. What research question was the class attempting to answer? So we have a rod outside and a rod inside. What type of research question do you think the class was trying to answer with this experiment? Will a physical change occur on either ion rod? Was there a chemical change or a physical change that occurred here? Chemical, the rust on the ion rod. So we can knock out that physical change. How often do iron rods rust? Well, we put one rod inside and one rod outside, so you do have a control, and that's good. So let's skip over B, okay? Will the iron rods inside gain mass when compared to the iron rods outside? All right, so we're talking about the rod inside that's not having anything happen to it, comparing it to the rod outside, all right? So it could be a mass change that we're working through. And then D, will there be a difference in the speed of the chemical change between the two iron rods? The rod inside isn't going to undergo a chemical change. So only one rod is undergoing a chemical change, guys. So we've already made it 50-50. Let's go through B and C again. How often do iron rods rust? Did they have a time frame in which they went and checked on the rods? They would have had to go out every day and really research and calculate how often that rod was rusting. So time really isn't a factor here. They even say several weeks later. That's not even an exact measurement. So when they say several weeks later, you can't think about time, okay? Because they're not even giving us a measurement for that. Our only answer choice is C. If you took both those rods inside and weigh them, you would see a change in mass, all right? Because the chemical change is occurring. You're adding elements to that iron. That's why it's oxidizing. Okay. Number 4, really easy one, guys. Which of the following pictures is an example of a chemical change? Since this is in black and white, I wanted to make sure that you can see what these pictures are. The first one is fire, all right? A. B is freezing, right? Glass freezing. C is cracking. And D is bubbling, right? Which of the following picture is an example of a chemical change? And remember, you need to look for multiple signs of a chemical change, okay? So first, let's go through fire. Well, when we have this fire burning, we can see light being produced. That's a sign of a chemical change. We can see that this wood is being turned into ash and smoke. You're not going to be able to get that wood back. So you have a clear substance changed as well. And we have an obvious temperature change. It's going to get very hot in there as well, okay? So right here, I can see a few different signs. Let's just say 3 different signs of a chemical change. Let's go to B. Well, we are changing the state of matter, but freezing isn't a chemical change. That ice is still just water. It's just frozen. And if you melt that ice, it would just be water. So freezing really isn't a sign of a chemical change. Let's go down to C, cracking. Well, obviously, we know this is a physical change, guys. You can put all those pieces back together and still have the original substance. Cracking, fractures, breaking, tearing, those are all physical changes. So it can't be B or C. Now let's go down to bubbling. Guys, bubbles is a chemical change. It's a sign of a chemical change. When you see bubbles being formed, that means that a pressure change is happening. But we know things that bubble, right? That aren't a chemical change, like soda. That soda is bubbling, but it's not changing chemically. It's carbonated water. So this could be just a glass of carbonated water. And the bubbles that you're seeing, all right, the carbonation. It could also be heating. They're doing it maybe in a clear glass, but this could be a heating element down here. And heating water, right? We'll put heating down here at the bottom. Heating water is just evaporation. You're not changing anything. If you captured all that gas, it would still just be water vapor, right? So it can't be D. Our only choice is A for a sign of a chemical change. All right. Number 5. Again, we're still going over chemical changes. In this example, Marlene's going on a camp out, and we need to recognize which of these examples is not a chemical change. Make sure you see that word "not." All right, because most of these are. So leaves on the trees turning green to red. That's a sign of a chemical change. It's a change in color. Those leaves are undergoing a chemical change. Right? They're getting different nutrients being pumped to them, and they're changing chemically. B, the campfire turning wood into ash. Well, you can't get that ash back into wood. So yes, a chemical change is taking place. C, the cloud forming rainwater from water vapors. All right. Well, if a water is evaporating, all right, it's still just water, correct? You're not actually changing anything. You're just changing the state. That's not a sign of a chemical change. But let's keep going through to make sure that we don't have any other ones that might be a physical change. D, a marshmallow turning black. Well, that's a color change, guys. You're burning that marshmallow. It's going to be a chemical change. So leaves turning green, chemical. Campfire being burned, chemical. Marshmallow turning black, chemical. Our only choice is C, all right? The cloud being formed, all right? Because that's just evaporation. Same thing with freezing, absorption, dissolving. Those are all just physical changes, not chemical, all right? Moving on to number 6. Which statement is most likely true? Explain the difference in these two pennies, all right? So I know it's hard to see, but the penny on the left is much darker than the penny on the right. So we need to figure out which one of these examples is the best explanation of this. They could all be explanation, but which one is the best explanation, all right? A says that the penny on the left has collected dirt. This could be true, so we're going to skip over it, okay? But it could have collected dirt. But let's see if we have some better answer choices. B, the penny on the right is made of copper. Well, as far as I know, all right, all of our pennies are made out of pretty similar substance. Now, back in the day, they used different types or different amounts of metal, but we're still using copper, all right? So I wouldn't say that these two pennies are made of different metals necessarily, all right? C, each penny was minted at a different location using different metal alloys. If you've ever been to U.S. Mint, you'll know that they're very particular about the metal alloys they use. That's how we can track and keep our money valuable, right? So C is not a good answer. And then D, the penny on the left has undergone a chemical change on its surface. Woo, look at chemical change, guys. Well, considering we answered every question today about chemical change, and considering that the STARS test loves asking about chemical change, and this is a major vocab word that we study multiple times, then D's probably our best choice. Sure, it could have collected dirt, but is that really anything to do with our science class? No. D has everything to do with our science class. All right, so chemical change will be for number 6. Okay. All right, number 7. Susan observes 2 antacid tablets dropped into water. Bubbles immediately form. When will she know that a chemical reaction has stopped? When she dropped that into the water, all right, you see a pressure change, all right, an unexpected pressure change. A solid into a liquid is causing it to dissolve, but it's causing an intense pressure change, lots of bubbles and fizzing. So when the bubbles have completely disappeared, that means no more pressure change is taking place, correct? That's a good answer, but let's move on to B. When the temperature of the water begins to decrease. A change in temperature is a sign of a chemical change. So if it starts decreasing, right, if a temperature change increases or decreases, that's a chemical change taking place still, so it can't be that one. When a white substance begins to form at the bottom, all right, formation of a substance, all right, precipitate, when 2 liquids come together and form a solid, or when you get a solid formed after a chemical reaction is taking place, that's still a chemical reaction taking place, guys. That's a chemical sign, so it can't be that one either, all right? Substance, all right, a new substance. So when heat is produced from the water, again, heat is a temperature change. And if a temperature change is taking place, it can't be chemical. All right, it has to be chemical, all right? A chemical change is still taking place. So our only choice is when the bubbles stop fizzing. And you can see that in a lot of our experiments we did at the beginning of the year. When the bubbles stopped, all the reactions stopped. It stopped changing temperature, it stopped changing color, it stopped fizzling. All the chemical reaction took place, and then we had our new substance. Number 8, which of the following piece of lab equipment is needed to measure the amount of heat energy released during a chemical change? How do we measure heat, guys? Now, I know this seems silly, but they put questions like this on the STARS test, all right? So look, we have something that measures our pressure. We have a microscope looking at small little objects. We have something that measures our mass. But which one of these measures temperature, guys? All right, we're not even going to explain that one because that's a thermometer. That tells you hot and cold, all right? But we love easy questions like that on the STARS test. They're easy points, okay? All right, very good. All right, moving on to number 9, guys. We're talking about chemical equations now. Now, we just got through with chemical reactions, but now we got to talk about chemical equations. So number 9, which of the following chemical equations for a reaction between carbon dioxide and water is considered balanced? Now, that's the key word there is balance. Remember, balance means that you have the same amount of atoms and elements on each side of the arrow. Remember, R, A, P, RAP. Reactant side, arrow, product side. These are your products, these are your reactants, all right? And plain and simple, you can just count out your elements on each side, okay? So first we have carbon, oxygen, and hydrogen. So write carbon, right? Hydrogen, and oxygen. All right. And we're going to figure out how many atoms of each element are on this side of the arrow. So let's go over at carbon. Well, we have 2 carbons in CO2, right? No, sorry, we have 1 carbon in CO2. Apologize. 1 carbon in CO2. When there's nothing after the letter, it means you only have 1 of them. Hey guys, show them the page we're working on, okay? Come on, get to it. We're on page 29 in our STAR booklet. That'll help you answer the day 3 in our STAR review, okay? I'll be done with this just a second if you have a question. All right, so when you're looking at 3 CO2, he says you have 3 molecules of CO2. There's 1 atom of carbon in this molecule, but there's 3 molecules. So 3 times 1, that means you have 3 carbon on the reactant side. What about oxygen? Well, we have 2 oxygens over here in this molecule, but there's 3 of them. So 3 times 2 is 6, but we still have some oxygens over here we can't forget about. There's 1 oxygen, all right, in H2O, but there's 6 molecules of H2O. So 6 times 1 is 6. So O2 times 3 is 6. O1 times 6 is 6. 6 plus 6 is 12. We have 12 oxygens. Now let's look at hydrogen. There's 2 hydrogens in H2O, but we have 6 molecules of hydrogen. So that means we have 12 hydrogen. And we're going to do the same thing for the reactant side. So let's write our carbon. Let's put our arrow so we know. We're going to write carbon, hydrogen, and oxygen. Count our carbon. We have 6 carbon right here. No other carbon in the equation, so that's 6. Already off the bat, do we have a issue here? We do. We only have 3 carbons on the reactant side, but we only have 6 carbon over here. We have 6 carbon here on this side. So we already know that this is unbalanced. And you'll repeat this process for B, C, and D. All right, so what I went ahead and did is I just wrote this down real quick, guys. We just broke down each answer choice. Now, when you got to B, you'll notice that when you broke it down, you had 6 carbons on each side, 12 hydrogen on each side, and 18 oxygen on each side. So we finally came across one that's balanced. But we're good test takers, so we continue to work through C and D to make sure that we didn't make any mistakes and that both of these are also unbalanced. So when you came across carbon, you do carbon on both sides, you'll see that right off the back, 3 carbons over here, 6 carbons over here, that has to be unbalanced. And when you come down to D, you'll notice right off the back, there's only 1 carbon over here, and there's 6 carbons. So we wrote that down, and that also has to be unbalanced, right? So if those are all unbalanced, our only answer choice, all right, is our balanced equation right here, B. Now, I know you could stop at B, guys, and answer that and circle that, but you'll never know if you had it correct if you don't check all of your answer choices, okay? Ladies, you're working on those 8 test questions. Come on. And gentlemen. Number 10, in question 9, what is the mass of the products compared to the mass of the reactant? All right, so it's talking about mass, guys. Mass is how much matter you take up, all right? You can compare it to weight to some degree, but remember, weight has to do with gravity. Mass has to do with how much matter you take up, all right? So A, the mass of the products is equal to the mass of the reactant. In a balanced equation, yes, they are equal, right? And B, guys, it's the third time, guys, please. Your final warning, okay? I don't have a pen, but I got a pen. Please, guys, those 8 test questions shouldn't take you any more than 10 minutes. Should be halfway through them by now. Thank you. Number 10, guys, in a balanced equation, the mass is going to be equal, right? You're going to have the same amount of elements on each side, same amount of atoms on each side. That means it's going to be equal. B, the mass of the product chemical reaction is always greater than the reactants. This is not true. In an unbalanced equation, it might be, but not always. C, some of the mass is lost in the reaction, so the mass of the reaction is greater. No, there is no reaction loss, all right? Remember, the law of conservation of matter says that matter cannot be created nor destroyed, all right? Has to come from somewhere. And D, there is not enough information. It depends on the condition of the reaction. No, there's always enough information. They give us all the numbers that we need in the formulas. That's how we know that A, C, and D do not exist. The law of conservation of matter says that these cannot exist. Either something happened, right, and the experiment was altered in some way, or this never happened at all. So the only answer choice, guys, here for number 10 is that they're equal. And guys, equal means balanced. Their only answer choice is A. On number 11, why is it important for a chemist to have a balanced equation for a reaction? Well, guys, again, the law of conservation of matter, nothing can be created nor destroyed. It has to come from somewhere, just like the law of conservation of energy. We studied that when we talked about Newton's laws. Energy can't come out of nowhere. It has to be created, has to be transferred into another form of energy. So why is it important to have a balanced equation? Let's see. She will need it to be able to predict the ideal temperature for the reaction to take place. Not having the right amount of reactants will cause the reaction to be unstable. In order to produce the desired amount of product, she will need to know the mass of the reactants to use. An unbalanced equation would cause her not to use the right lab equipment. All right. So unbalanced equations, they don't really exist, guys. So we can take that one out automatically. If she is trying to produce a product, right? If she's trying to produce maybe 100 grams of a product, then she does need to know how many grams of reactants to start with. You start with 100 grams, you end with 100 grams. So that sounds pretty good. Not having the minor reaction won't necessarily cause it to be unstable, all right? Because if you're mixing different amounts of reactants, yes, right? If you're mixing different amounts of reactants, yes, but it's not going to make it necessarily be unstable. She'll need to be able to predict the ideal temperature for the reaction to take place. Now, if she hasn't tested these chemicals in smaller amounts, she's not going to know the temperature that needs to take place. In order for this to work out, temperature is not really going to matter here, okay? So our only answer choice is C. Because remember, you always end up with the same amount of what you started with. So that's how you need to know your chemical equation is balanced and it exists. All right, last one right here, number 12. A beaker with 2 liquids compound is placed on a hot plate and heated. What question can best be answered from this experiment? All right, so 2 liquids compound is placed on a hot plate and heated. We're trying to figure out maybe that these things react, maybe at a certain temperature. Which substance will float on one another? That might have to do with density, right? Which substance will freeze first? Remember, this is going to be a sign of a physical change, right? Freezing. Which substance will conduct electricity? Well, there's no electricity here, guys. There's heat. It is energy, but this is heat, not electricity. So it had nothing to do with our freezing because it's heating, right? We're heating the water, we're not cooling the water down. Density has to do with float, but we're obviously changing the temperature and we have 2 different liquid compounds in there, all right? So we're trying to create a reaction. But guys, what have we been talking about all day through this, day 3? Chemical reactions, okay? if we were trying to figure out which substance would float, guys, we would just have to figure out its density, right? The compounds would separate themselves pretty quickly to show that anyway. All right, our last spot for today, guys, is going to be our vocabulary on the very back, all right? So we're just going to go through. Guys, you're supposed to be halfway through that. Go. All right, we're going to go through our vocabulary real quick, just 1 through 8, just a few vocab whenever we're talking about our chemical formulas and chemical equations. All right, so just moving on to our vocabulary, guys. We're just going to go over. Nah, you're good. We're just going to go over 1 through 8 real quick. So number 1, the new substance produced from a chemical reaction and are written on the right side of the chemical equation. Remember RAP, R-A-P. We have our reactants, arrow, then products, all right? So products are going to be on the right-hand side. A change in temperature, state of matter, shape, density, or any other observable characteristics of a substance, all right? So whenever something changes, all right, and we can see it, all right, this would be our physical change, right? So good, E, physical change. Next, a chemical equation that has an equal number of types of atoms on the reactants and product side. So equal is the key word there, equal number. That means you're balanced, all right? It means you're balanced, A. A change when a new substance is formed from the reaction between 2 or more different substances. New substance, that's going to be a chemical change, guys, chemical change. The process in which physical and chemical properties of substance are changed when a new substance are formed, all right? This itself, all right, is going to be a chemical reaction when things are actually changing. See. 6, the principle that states of mass of a substance before reaction is equal to the mass of the substance after the reaction. This is a law of conservation of mass, guys. Matter cannot be created nor destroyed. It has to come from somewhere. The substance in a chemical reaction that are being changed into a new substance, what do you start with, all right? That are being changed. What do you start with in a chemical formula? You start with your reactants. And the number that precedes the chemical formula that indicates the number of molecules, remember the big number in front precedes the big number in front. These are called our coefficients, all right? Subscript is a tiny number after, but coefficient is our big number that tells us how many molecules we have. Great work today. Make sure you don't forget to put your name and date on those pages so we can always keep track of when you're able to complete it. Thank you so much. As always, hit that bell icon, like and subscribe, and have a good day.